Okay, any questions?
I have a question about the concept of currents. Actually, it's about the charge in a current carrying wire for a distance. Can we assume that zero because the amount of charge are entering and exiting are the same?
Well, the change in the amount of charge is zero. You see, we have this continuity equation. Well, just because the amount of current entering is equal to the amount of current leaving, the divergence of J, if you integrate it over the surface of your region, it is zero. So rho, the total rho, that is the total charge, is not changing. But it doesn't tell me that the total charge is zero.
So what about, actually I use another approach. I slice the wire into infinite small thickness slabs. So actually it's always valid, the amount of charges are entering and exiting are equal. So the slab has no ability to accumulate charge.
Well, that is because we are in statics, yes.
Even there is a current flowing.
True.
The slab. If we integrate the charge of the slab along the wire, it gives us the total charge zero again.
Not the total charge, I repeat. It's the total charge is not zero, but the change in total charge is zero. You see, let's just look at this example. I mean, there was a point which I didn't really stress when we were discussing the current density. We said that, okay, so this is my wire. There is a current running through my wire. The current is made up of charges. So if the wire has a linear charge density lambda, and if the charges are moving with velocity v, we said that, okay, the current is just lambda times v. This is how we call the current. Now the thing, if you look at this wire is carrying a current. I is non-zero, but the linear charge density of this wire is zero. There is zero charge here. But still there is a current running through it. Now the thing that I didn't really pay too much attention to is if you just take this wire, it is neutral because the linear charge density of positive charges is equal to the linear charge density of negative charges. Well, the current for this wire would actually be, well, the positive charges have some velocity, and the negative charges have some other velocity. So this is a system which has two different kinds of charges, and each kind of charge has a different speed. So the total current running through this wire is just the sum of the currents that is carried by the positive charges and also the negative charges. Now for a wire at rest, the positive charges are the nuclei basically. So V plus is zero. So I is nothing but the current is determined only by the negative charges. So here in this expression, what we should stress is that this lambda is the charge density of the moving charges, and V is the speed of the moving charges. So this wire is neutral, not because the current entering and current leaving are of a given segment are equal, but mainly because at a given segment, the amount of negative charges is equal to the amount of positive charges. But since the amount of charges entering a segment, which will be negative charges entering that segment, and the amount of negative charges leaving that segment are equal, the total amount of negative charges in this segment is not changing. So the total number of negative charge in this segment is always the same, and it's always equal to the total number of positive charges, so the total charge is zero. Yes, other questions? We we were discussing the solenoid on Wednesday.
Ondan önce şey yapmıştık ama böyle.
Infinite.
Plane vardı.
We had the infinite, well, the infinite plane was last week, I think. We had the infinite wire.
İşte geçen hafta Cuma infinite plane yapmıştık da bitmedi.
Oh, we didn't finish it. Okay. Okay, so let's first start with the solenoid example. Let's continue with the solenoid example. That was what we were doing on Wednesday. Let's calculate the vector potential of the solenoid. And then after the solenoid, we can go back to this infinite plane example, calculate the magnetic field, calculate the vector potential corresponding to this infinite plane. Well, we first looked at the magnetic field created by the solenoid. The solenoid is basically, you can think of it as a cylinder, ideally an infinite cylinder where current wire is wrapped around it. It basically has this shape. So the current is running in this direction. Or if we just take a cross section, in the cross section, the current is coming towards you, goes around the circle, goes inside, and then just completes this turn. And ideally, it's not just some sparse wide loops, but they are very densely wound wires around it, so there are no such gaps in the wires. And we said that the magnetic field line, the B field line, will be horizontal. And if it goes to infinity, the magnetic field lines will be non-zero only inside. There will be some lines inside, no lines outside. So outside B would be 0. And then we said, okay, so we know something about the B field. We can use the Ampere's law, B dot dl, integrated over around any closed loop. This should be equal to mu0 times the total enclosed current in the wire. And then we said, okay, so B is 0 outside, B is horizontal inside. So we can take such a loop let's say A, B, C, and D. Let's go around the loop in this sense, in the clockwise sense. Let's choose this axis, the horizontal axis, to be our z-axis. This is our z-axis. So B dot dl will be, okay, from A to D, B dot dl. From D to C, B dot dl. From C to B, B dot dl. And then from B to A, B dot dl. So this integral, I just divided into 4 parts corresponding to the 4 sides of my rectangle. And then we said that as we go from D to C, in this region, inside the cylinder, dl and B are perpendicular to each other. In this segment, B is 0. So in both cases, B dot dl will be 0 along this path. Along this path, as we go from B to A, again, inside this our solenoid, B and dl, they are perpendicular to each other. Outside, B is 0. So along this segment, B dot dl is always 0. From C to B, B is 0, so B dot dl is 0, which basically tells me that these 3 integrals from D to C, this is 0. From C to B, this is 0. From B to A, this is 0. So all those 3 integrals are 0. The only contribution we have is from A to B. Now, from A to B, we know that the B field is along the z-axis, either positive or negative z-axis. So let's just say that B field is, it can depend on S, the distance from the center of the solenoid. It cannot depend on Z, on the Z coordinate, because we have translational symmetry. Nothing changes as I change. Nothing should change as I change the Z coordinates of my points. It cannot depend on phi coordinate. I'm taking a cylinder, so if I rotate my system, or if I change the phi coordinates of my point, nothing should change. So B can at most depend on S. Well, we will see in a moment that it also is independent of S. But just from the symmetries of our problem, we know that B might depend on S. It cannot depend on other coordinates. Now, from A to D, my dl vector is in the direction of z, in the z-hat direction. So dl is equal to its magnitude in the z-hat direction. Now, B dot dl from A to D is then Bs times dl. And which basically tells me that this B dot dl integral, I can write it as from A to B, Bs times dl. But you see this A to D line is parallel to the central axis. So its distance from the central axis is constant. It doesn't change from point to point. And well, its distance from the central axis is what we call the S. So as I go from A to B along that line, along that straight line, S is constant. So I can just take it out of my integration from A to B of dl. If we call this length of the rectangle as capital L, that integral over here is nothing but the total length of the AB segment, which is Bs times large L. Then we know that there is a current running through it. Let's say there are n wires inside my rectangle. Each one of those wires carries a current I. Let me just call the current I. There are n wires going through my rectangle, so the enclosed current is n times I. Well, of course, it can be positive or negative, and we have to determine it by using the right-hand rule. Just take your right hand, curl your fingers in the direction of your loop, then your thumb points in the direction of the positive current. And for this counterclockwise, if we go around our loop in the counterclockwise sense, the positive direction of the current is into the screen. So it is the enclosed current is plus n times I, not minus. If we had chosen our loop to be in the counterclockwise sense, then the right hand just tells me that the positive direction of current is out of the screen. So, and in that case, the current would have been minus n times I. But for this sense of the going around the loop, it's plus. And this basically tells me that this Bs is mu 0 n over L times I, or mu 0 small n times I. And small n is the number of turns per unit length. One thing, Bs turned out to be positive. You see, we didn't assume that Bs is positive. Of course, to start with, I know that the magnetic field should have been in the plus z direction. But in this derivation, I never assumed it to be in the plus z direction. But at the end, it turned out, since Bs turned out to be positive, and my B field is Bs times z hat, B field, as a result of my derivation, B field turned out to be in the direction of plus z. Now, the next thing is, what about the vector potential? So now we know the magnetic field. B field is in the z-hat direction. It is mu 0 times n times I if S is less than the radius of my cylinder. And it is 0 if S is larger than the radius of my cylinder. And this should be I should find some A such that this is the curl of A. Now, of course, there are infinitely many possible values of A, so we can just choose one of them. Now, most of the time, the vector potential, the properties of the vector potential reflect the properties of the currents that's creating the vector potential. So in this problem, the current is rotating in the phi hat direction. You see, in this, the current is rotating in this sense. This is the phi hat direction. So most probably, we can find a vector potential that also rotates in the phi hat direction. So I will look for an A, which is in the phi hat direction. And, well, again, just due to the symmetry of my problem, I'm looking for an A that doesn't depend on Z. It shouldn't depend on phi. It can only depend on S. This is just a guess for the time being. So I'm assuming that let's try to find, I'm just saying that let's try to find the vector potential of this form. Will I be able to find such a vector potential? We will see. I mean, if it doesn't work, if I cannot find such a vector potential of this form whose curl gives me my B field, then I should look for some other vector potential. So let's first try this one, and if we fail, we can try some other A fields. And in cylindrical coordinates, the curl of A, we can write it as 1 over S del over del S, S times A in the Z hat direction. Now that is fine, at least. I mean, we know that the B field is in the Z direction, so this curl of this vector potential is also in the Z direction, so that's nice. And there's 1 over S del over del S times A should be equal to mu 0 n times I if S is less than R, it is 0 if S is larger than R. These are my conditions. Now let's try to solve this equation inside my cylinder first. For S is less than R. 1 over S d by ds, well, A, that function A, the Z component of my vector potential, the phi hat component of my vector potential, depends only on S, so that partial derivative is actually a total derivative. I also will just go to a total derivative notation. S times A, this should be equal to mu 0 n times I. D by ds of S times A is equal to mu 0 n I times S, or S times A should be equal to mu 0 n I times 1 over 2 S squared plus some constant. I don't know that constant yet. And so A of S inside my cylinder is 1 over 2 mu 0 n I times S plus some constant over S. So we see that inside my cylinder, the vector potential increases linearly with S. Now for S larger than the radius, so for a point outside my cylinder, remember there is no magnetic field over there. 1 over S d by ds, S times A should be equal to 0. Well, this tells me that S times A should be a constant. Let me call that constant D. So A should be equal to D over S. As long as this is my A, note that whatever C and D are, this is a possible choice of my vector potential. For any value of C and S, C and D.
Hocam peki S eşittir R durumunu niye almıyor?
Now we will consider that case. Now we want A to be continuous. Because if it is not continuous, the derivatives would include some Dirac delta functions. That is not something we want. So the A should be continuous. So this is A for S larger than R. So this tells me that A at S is equal to R is continuous. This is one condition, which tells me 1 over 2 mu 0 n times I R plus C over R should be equal to D over R. This is one condition I have. The other condition, A at S is equal to 0 is finite. At the center of my solenoid, it should be finite. Well, that tells me that C is equal to 0. This tells me that C is equal to 0. The previous result tells me that D should be equal to 1 over 2 mu 0 n times I times R squared. No, there is no D over R. You see, D is relevant outside my cylinder. You see, there is no D over R. Inside my cylinder, this is my vector potential inside my cylinder. For it to be finite at S is equal to 0, C has to be 0. But this is always finite in the region when S is larger than the radius of my cylinder. So now I have my vector potential. This is equal to, it is in the Z direction. No, it's in the phi hat direction, sorry. For S larger than the radius, it is 1 over 2 mu 0 n I R squared over S. And for S is less than, for inside the cylinder, it is 1 over 2 mu 0 n I times S. No. You see, one thing when S is equal to R, these are equal to each other, as they should. Now we had an S squared here, but this is S times A, which contains the S squared. So I have to divide by A. I have to divide by S, so I end up having a term linear in S. True. It's D over S, D for some constant D. Then we said we have two conditions. One, the A should be finite everywhere. Well, since A is finite everywhere inside, including the horizontal axis, the central axis of the solenoid, well, the solenoid is inside my cylinder. So inside my cylinder, this is my vector potential. This should be finite when I set S is equal to 0. That tells me that this term shouldn't be there, which tells me that C is 0. So from the finiteness of the vector potential, I conclude that this coefficient is 0. Then I know the continuity of the vector potential. The vector potential should be continuous. But the continuity of the vector potential just tells me that if I approach the surface of my cylinder from inside, then the vector potential is this one with C equal to 0. Or if I approach the surface from the outside, it is this one Just I put S goes to R from outside. These two should be equal to 0, equal to each other. So C is 0, forget this term. So these two terms should be equal. And hence D should be equal to 1 over 2 mu 0 n I times R squared. So that tells me what D should be. The term is not constant. The coefficient is constant, yes? Well, you see, S is the distance from, I have this, my solenoid, it has a central axis, and the vector potential, let's say outside my, inside my solenoid, is this one. How did we obtain this one? We obtained this one by requiring that the curl of this should be equal to our magnetic field inside in the z direction. This was our requirement. But we have other conditions on A. Not just that B should be equal to curl of A. We are not looking for an arbitrary A. I'm looking for some A that is, let's say, finite everywhere. That's a condition that I impose. So that tells me that you're right, this is just a constant, but this term as a whole is infinite along the axis of my cylinder. And I don't want that term. I know that whatever this value of C is, the curl of this term is always equal to my B field. So whatever the value, even for C is equal to 0, it satisfies that condition. But then, for C is equal to 0, it satisfies my additional condition that A should be finite. So that is why I set C equal to 0. Well, I cannot set D equal to 0 because, you see, A field satisfies the continuity condition also. It has to be continuous. And that tells me that D cannot be just arbitrary. It should be equal to this coefficient times R squared. And just keep in mind, these two solutions, this solution I obtain inside my cylinder. This solution I obtain outside my cylinder. What about the solution on the cylinder? So to have a meaningful solution on the cylinder, A should be continuous. Now, what is that one? You see, D over R is equal to that one. So D is 1 over 2 mu 0 n I R squared. Now, of course, I claim that A should be continuous. How do I know that A is continuous? Now, let's prove the continuity of A. You see, what do we know? B should be equal to the curl of A. But this tells me that if I integrate curl of A over some area, this should be equal to the integral of B over that area. Well, the integral of B over a given area is what we call flux. Well, the integral over an area of the curl of a vector field, we can write it as the integral of the vector field over this closed loop, which forms the boundary of my area. So I have this condition. A dot dl over any loop should be equal to the magnetic flux passing through my loop. Now let's consider any boundary. It can be some physical boundary, some hypothetical mathematical boundary, etc. And let's consider my integral of A dot dl across this loop. Let's say this is the height d. In the limit as d goes to 0, you see the flux is magnetic field times the area. As d goes to 0, the area goes to 0, so the magnetic flux goes to 0. So as d goes to 0, this integral should be 0. Well, this condition tells me that a tangential component of A, the change in the tangential component of A across this surface is 0, or A tangential is continuous. You see, it doesn't really tell me that the vector potential A is always continuous. But it just tells me that if I have a surface, then the component of A tangent to the surface should be continuous. In our problem, we have this cylinder. A is in the phi direction. So A doesn't really have a perpendicular component. It only has the tangential component on the surface. So A has to be, A itself has to be continuous in our case.
D sıfıra giderken A dot D ile sıfır dedi. Ama şu alt ve üsttekilerin etkisi olmayacak.
That is why they have to cancel each other. That is why we have this continuity. The A from this part, the A dot dl from this part should cancel the A dot dl from the lower part. That's why they have to be equal. Well, this is 0 because it's the flux. You see, let me just add one more step over here. This is always equal to the magnetic flux. Magnetic flux goes to 0 as d goes to 0. And as d goes to 0, there is no contribution from these sides to my integral. The only contribution is from the top and the bottom, from these longer sides. And since they have to be 0, their contribution should sum up to 0. They have to cancel each other. Well, one is in one direction, the other one is in the opposite direction. So what I obtain, A dot dl over this loop, is just A outside minus A inside. Let's say this is the L hat direction times L hat times L. This should be equal to 0. L is this length. This is basically my dl. dl vector in the outside is in the L hat direction. The L vector on the other side is in the minus L hat direction. So that's why I have this minus side. So their horizontal components should be equal on both sides. But that is the definition of continuity. So the tangential component of A has to be continuous.
Bu her zaman geçerli mi? Eşit olması.
Well, this is our proof. So what did we do over here? This equality is always true. That's the definition of the magnetic flux. And on the left-hand side, we just use that the curl of A integrated over an area is equal to A dot dl. So this equality is always true. If we have an arbitrary surface, we can always use this relation for such a loop. Part of the loop is in one side, part of the loop is on the other side. As we take the d goes to 0, the flux will always go to 0 unless b is infinite. As long as b is finite, the flux, remember, is the magnetic b times the area. As long as b is finite, if area goes to 0, then the flux goes to 0. This is always true. Well, in the limit that d goes to 0, I can always write this integral in this form for sufficiently small l. So this will always true. I didn't make any assumption except then the finiteness of B. That's the only assumption I made here.
O zaman hocam buradan discontinuity yazabilir miyiz?
This is the continuity we have. Only the tangential component of A is continuous.
Yani şunları birbirinden çıkaracağız. Şu bulduğumuz.
I don't, you see what this continuity tells me, either you can look at the difference or just write A inside that L hat should be equal to A outside that L hat. Just take a horizontal vector, horizontal to your surface. Take the horizontal components of A both inside and outside. They have to be equal. Well, back to our problem. A is in the phi hat direction. Phi hat direction is tangent to our surface. So A is already tangential. It doesn't have any vertical, any perpendicular component. So A has to be continuous. A on one side should be equal to A on the other side. So that is what we wrote over here, this relation. This is what I obtained A for inside my cylinder on the cylindric surface. This is the A I obtained outside my cylinder.
Şimdi A direction'ında dedim. Yani mesela D buna tam dik oluyor. Öyle. Bu D şey mesafesi aldık ya.
Okay.
Bu L'e değil. Yani o yönde hiç direction yok mu L'in?
No, I didn't say there is no direction. I'm just sending it to zero. So since this relation is always true, it's also true when I send D is equal to 0. I just cannot say anything for the component of A perpendicular to my surface. I'm just saying that I cannot say anything. I only obtain a result for the parallel component.
Yani sadece paralel olanlar birbirine işte.
Yeah. The parallel components are equal. The A can have a vertical component on the surface. They might not be equal to each other. At least just using this argument, I cannot say anything about that.
Hocam biz burada şimdi D'yi sıfıra götürdük ya. L'yi sıfıra götürseydik ne olurdu?
You get 0 equal to 0. Nothing. It's true, but it doesn't tell you anything. Well, what can I say about the perpendicular component? You see, we talk about the horizontal and the perpendicular components using the curl and the divergences. If you know the curl of something, you can say how the parallel component changes across a given surface. Like the curl of the electric field was 0, which tells us that the parallel component of the electric field should be continuous across a surface. And we also know the divergence of the electric field should be equal to rho over epsilon 0. And from this, we could derive we could conclude that the perpendicular component of the electric field will be discontinuous, and this discontinuity gives us the surface charge density. You had several homeworks to calculate the surface charge density using the discontinuity of the electric field. So if you want to say something about the discontinuity of the perpendicular component of the electric field. Now, to say something about the perpendicular component of the electric field, we have to know the divergence of A. What is the divergence of A? We chose it to be 0. Remember, we said that for a given B, there are infinitely many possible choices of vector potential. In order to just pick up one of them, we just impose the condition that the divergence of the vector field is 0. Well, we know that we can always find such a vector potential. If you go back to our discussion, we said that A0 and A, they would correspond to the same B field if they differ by the gradient of some function, because the curl of the gradient is 0. And we can always find some F for any A0, which doesn't necessarily satisfy this condition. If A0 doesn't satisfy this condition, we can always find an F such that A satisfies this condition. So we are looking for vector potentials whose divergences are 0. So if we integrate the divergence of A over some volume, well, divergence of A is 0, so its integral is 0. But at the same time, this is nothing but the integral of A over any closed surface. This should be also equal to 0. So go back to our boundary. We have to choose some closed surface. And just to study the continuity properties, we choose a cylindrical surface. This is D. This is D. So A dot ds in the limit as D goes to 0. Let's say this area has total area S. Let's call this as our normal direction. This is the outside. This is the inside. In the limit as D goes to 0, there won't be any contribution from the sides. I only get a contribution from the top and the bottom. The area vector of the top area is in the direction of N. So this is A outside minus A inside, scalar product with N times S should be equal to 0. So this tells me that A outside dot N should be equal to A inside dot N. So we had already said that just using the finiteness of B, the vertical component of A, the horizontal component of A, or the component of A parallel to the surface should be continuous across the surface. Just using the fact that the divergence of A is equal to 0, it tells us that the component of A perpendicular to the surface, that is in the direction of N, should also be continuous. Since the perpendicular component is continuous, horizontal component is continuous, so the vector potential is continuous. But keep in mind that not all vector potentials are continuous. Only the vector potentials that satisfies this Coulomb gauge. There are infinitely many vector potentials corresponding to a B field. Some of them satisfy the Coulomb gauge. And these vector potentials that satisfy the Coulomb gauge, they are continuous across any boundary. They have to be continuous across the boundary.
Yani bu yönden mi konuşuyoruz, böyle mi konuşuyoruz?
Yes.
Başlangıç noktası neresi peki? A vektörü nerede başlıyor?
The vector is at every point you have a vector. We are not talking about a line.
Yani böyle.
At this point there is a vector. At this point there is another vector. What this continuity tells me is that just imagine any surface and take a point on this surface. I can come from a point outside, come to that point. At every point, remember, there is some vector, A. I come to that point and cross this surface and go to the other point. As I'm moving along my curve, this A vector at every point changes continuously. It doesn't jump. For example, in the case of the electric field, if there is a surface charge density, let's say, we know that the perpendicular component of the electric field will not be continuous. So if we just follow the electric field along a path, let's say it is pointing in this direction, its direction is changing continuously, then it reaches my surface, and suddenly as I cross my surface, the electric field from this direction, it will go to this direction. There will be a sudden jump in the electric field as I'm crossing my surface with a surface charge density. But this tells me that for the vector potential A, this jump doesn't happen. By the way, this method also tells me the fact that the A dot ds is equal to 0 and A dot dl is equal to phi b would allow me to calculate the vector potential in a different way. So you see, up to now we have seen, we integrated the current density to obtain the vector potential in the case of the infinite wire. That is one way of obtaining the vector potential. In this problem, we found the B field first, and then once we know the B field, we try to find a function A whose curl would be equal to our A, our B. Now we can also try to determine A by just using this, well, this will be enough in fact, by using these two properties. That we will do after the break. Now, any other questions? So see you after 10 minutes.